Let's see.
Please proceed. I have started the recording as well, with your permission.
Sure. So the title of my talk is Topological Materials. I'll try to give an overview of topological materials. I've tried to keep it at a level, sort of an introductory level. And I hope it will be useful for the audience, and it's being recorded. So probably more people will be able to benefit. Go to the next slide. All right. All right. Now it's okay. So let's start big picture goal. And we're always, when we're studying and trying to understand it, we're looking for some organizing which are unique. And the aim is to understand and these basic principles, and also to utilize in ways which are useful and beneficial for humanity. So we'll see that there are two ideas. Symmetry will play a major role in the talk that I'm presenting today. Both of these are deep ideas. Role of symmetry has long been. Role of topology in advanced matter physics has appreciation of it is more recent. Can you guys hear me all right? Is the sound okay?
Yes, perfect.
Yes.
Perfect.
Right. So topology's role is more recent, and come together when we classify and try to understand the properties of materials. And that will be the focus of today's talk, and I'll try to convey the role of symmetry and topology in this regard. So condensed matter physics, for those who are not, I mean, this is a condensed matter session, so all of you know, but just to set the stage, essentially it deals with condensed phases of matter. It's the study of condensed phases of. And when we define condensed phases of matter, talk about systems with degrees of freedom that are strongly interacting. And to view an intriguing phenomena, wide range applications, and question that we address among others is phases of different materials, different condensed matter systems, and how do you drive systems from one phase to another? Parameters like temperature or pressure or doping, or drive system from one phase to another. And one of our major goals is to figure out how these phase transitions occur and phases under certain conditions. The traditional theory of has been Landau's symmetry breaking theory, and among the universal organizing principles, symmetry is one of those. And in Landau's symmetry breaking theory, it plays pivot. And most phases of matter can be characterized and understood, and between different phases can be understood in terms of Landau's symmetry breaking theory. Now, the basic content of Landau's symmetry breaking theory, it basically says because they have different symmetries. So, yeah. So a phase transition is a transition accompanied by a change of symmetry. So you go from one phase. For example, if you are in a certain phase, if you lower the temperature, you go to another phase. And symmetry breaking theory tells us that there's a change to go through phase transition. So as I said earlier, up till the 1980s, in the condensed matter community was that most of the phases for matter can be characterized and understood by using symmetry breaking theory. But in the 1980s, certain experiments revealed that more is required, And we'll see that topology plays a fundamental role there. So an important quantity in Landau symmetry breaking theory is what is called an order parameter, and characterizes the broken symmetry state. And usually an expectation value of some physical observable. And it's a local quantity, and near the critical point where the phase transition occurs, we have to expand the free energy in terms of the order parameter. And that's the basic theme of Landau symmetry breaking theory. As an example, I mean, probably useful more for students, that if you look at this one-dimensional chain where each side can have spin up or down. So this is I've just drawn a configuration of spin. This is what is called a ferromagnetic Ising model. So the spins can only have two configurations, spin up and down. If we can say take a spin as +1 and -1. So in this model, the basic Hamiltonian is what is known as a ferromagnetic Ising model. So you have a spin, have a coupling, which sets the energy scale, which we take to be positive. And if the spins are, if you see that if the spins are aligned, then in this case, you'll have the minimum energy. So explain what symmetry's role is in this case. Consider this transformation, that if you transform or flip all the spins on this chain, then the Hamiltonian doesn't change. Because if you flip all the spins, there's a minus sign that comes from there, and there's another minus sign that comes from the second term. And both of these minus give you 1, +1. So the Hamiltonian is what we see invariant under this transformation, which is the flipping all the spins. And so any state can be expressed in terms of the spin configuration, spin up and down. So you can have 2 to the n different configurations. I've just drawn 9 spins here, but you can have any number. And the larger number, it will make more sense to talk about phase transition. But if you look at the ground state, the minimum energy state of these spins, it can only be with all the spins are aligned, either up or down, because here we allow only 2 configurations, up and down. So these 2 states have the same energy. But the important fact is that under this transformation, these 2 ground states are not invariant. They do not remain the same. In fact, if you flip all spins in the first one, which I'm calling 0, 1, you go into 0, 2 state. And if you do the same with 0, 2 state, you go to 0, 1 state. These states, the ground states, are not invariant under this transition, whereas the original Hamiltonian, this describing spin chain, which is a ferromagnetic Ising chain, is invariant. This is the basic, I'm trying to convey the basic concept of symmetry breaking, where the Hamiltonian under a certain symmetry transformation does not, but the ground state of that Hamiltonian changes under transformation. It does not remain invariant. This is a simple example of role of symmetry and breaking of symmetry, and it's trying to highlight that. And you can also define a parameter here, which would be a magnetization. So in one phase, think of it as like a temperature phase, which is a paramagnetic phase, where all of these have random orientation. Orientation random meaning they can only have 2 states, up and down. But there'll be random configurations of up and down spins. We would characterize as a paramagnetic phase. If you lower the temperature, the system would go of these the energy degenerates, and that would correspond to the many-body ferromagnetic state. So there's a phase transition, and it can be characterized by an order parameters such as magnetization. So this simple example illustrates the concept of symmetry breaking and order parameter fundamental to Landau symmetry breaking theory. Yeah, now it was realized a few years back. As I said earlier, Landau symmetry breaking theory has been there for quite some time, been very successful. But when more recently we realized that there are phases and phase transitions that cannot be created by land or symmetry breaking theory. And today, I'll mostly be concerned with electronic phases of matter and most uh, insulators, topological insulators, semi-metals, and to some degree superconductors. And we'll see that these models require something beyond symmetry breaking theory. So coming to that, important new ingredient and important new deep idea that makes its appearance is the role of topology. And topology is a branch of mathematics that studies shapes, not change under continuous deformation, including stretching and bending, are what are known as topological in nature. So just to illustrate this point, if you think of this sphere made of rubber, and you this and making this continuous deformation without on gluing together, which is not allowed. You should keep making these. You'll see that all of these objects can be connected to each other. The shapes can be connected to each other through deformations. But when you reach here, what is happening here is that hole is being generated. That can only happen if you cut this object here and then glue it together. So there's a sort. This is not a sort, but actually a change in topology here. So you can think of these shapes falling into one topological class, and then with this one here and all of these here falling into another topology. This is how topologists define different topological classes and characterize different shapes. But when you go here, you have two holes which can be connected with this object here. So you have to go to another. His object belongs to a separate topology. And an important theorem is what is called the Gauss-Bonnet theorem. And it's a very important and deep result and beautiful result. Is that if you look, K here is the Gaussian curvature. So if you in curvature and integrate it over the surface, closed surface sphere, what you obtain is value here. On the right, G is what is called genus. Basically represents the hole or a handle in an object or a shape. So for a system, so this result is 2, which is integer value. So what you see, local quantity, which is the Gaussian curvature, integrated over the whole closed surface, closed manifold, you get an integer valued quantity on the right hand side, which is invariant. So for an object with no holes, has a particular integer value. And locally, if small insect moving on this surface, locally it would not be able to tell the difference between this object here, which is a sphere, and a torus here. But if you look at the global property in the sense of integrating the Gaussian curvature for this surface over the whole surface with genus 1, you get 0 here, so another integer. So you have an object with an integer value of this invariant 0 on the left, and you have an object on the right, you have 0, and on the left you have one with integer value 2. So they belong to two different topological classes. And the theme that we will see in this talk is that you take a local quantity, you integrate it over a closed surface. Now we're talking about a real world surface of a sphere, but it does not necessarily have to be a sphere. It can be the Hilbert space of quantum mechanical states act as surfaces. And we'll see that that will be very important because something local integrated over the whole surface gives you an integer valued quantity, which is called a topological invariant. And you know, when you have an integer, you cannot continuously change it. It has to take values from one integer to the next integer. So you can only go from 2 to 1 or 2 to 4, but you cannot change it continuously. So the question is, what is the role of topology in characterizing phases of matter? And for that, we have recently realized in the last decade or article that there's an extension of our usual band theory is required. So, which is nowadays called topological band theory, and that helps to characterize these phases of matter, which are called topological phases of matter. So, just a quick reminder that when we deal with condensed matter systems, which are translationally invariant, for example, crystalline solids, band theory plays a very important role. And so in the band theory, the electron states are no longer plane wave states, but they're block states. So that's very important if you have a system which is translationally invariant, like a crystalline solid. So the electrons treated as free particles, and we neglect interaction between the electrons. All the effect of the lattice potential is accounted for in these block functions. And band theory has been very successful explaining differences between metals, insulators, and semiconductors, classifying and characterizing them and their properties. So what has been realized recently is that there are phases that can be characterized by the topology of the state vectors, essentially these block functions. So we'll be looking at twists of these block functions as we change some parameter, and that parameter would be the crystal momentum. And so that would be where we are headed in this talk. I'm going a little fast here so that probably a lot of people are familiar with. So in a topological phase, what we'll find is that the physical response functions are quantized. They have these integer values in terms of some quantity, have integer values, and they're robust. It's hard to, change those, and we'll example of those. And they will become clear as we go forward. So, these will be our topological invariants. So we need an extension of our usual conventional band theory, and what we require is what is known as a topological band. And what we'll find is that the topological band theory, we have, when we construct these topological invariants that are helpful in characterizing topological phases of matter, require local quantities which is Berry phase of all bands. So Berry phase plays a very important role in this whole characterization. Topological invariants will be expressed in terms of these of occupied bands. So I'll introduce quickly what Berry phase is, and what that requires is of a background in which most of us are familiar with quantum physics, is the adiabatic evolution of states. So if you have a Hamiltonian which depends on some parameter, which is a function of time, so it's a time-dependent Hamiltonian. Usually when you start the system in some initial state and the system is governed by a time-dependent Hamiltonian, what would happen is that generically system would transition to. So if you start in some state n, it can transition to state m. But in the adiabatic approximation, what you do is where you don't want the system to transition to this. So you only allow for very slow variation of the Hamiltonian, very small change in the Hamiltonian. So in this case, you vary this parameter R of t slowly. And how do you characterize how slow or fast? it is related to the difference in energy or initial state and the adjacent levels. So let's say you're in state N, and there's an adjacent level M. So ground state, think of the first excited state. So this time scale gives you a scale for slow variation in the parameter slowly in time. So your Hamiltonian is changing slowly. In that case, there will be no transition from to some other state. So there will be no mixing of states. So in uh, non-degenerate ground state, which is labeled some index n. So if the initial state is phi n of t, it will still be in the same with the same quantum number, but it will be an instantaneous state of the Hamiltonian psi n of t. So the state will, and these are the phase factors that come evolution. This is the dynamical phase, and the other one, gamma, is what is known as the Berry phase. So this initial phase is very important. And in the early days, people thought that since parameter path, it is not gauge invariant, so it's probably, but it was realized that if you do it over a closed loop, evolve the system adiabatically over a closed loop of parameters, then it is gauge invariant. And this factor can be expressed in terms of what is known as Berry connection. I'm calling the parameter K in this slide because I'm thinking that we'll be talking about wave as the parameter. So the Berry connection can be expressed in terms of these state vectors, and one can also determine curvature as the curvature of the Berry connection. You see this expression is the and of with A and omega this to electromagnetisms, and you see that you as a vector potential in momentum space case. This is as a magnetic field in K space, and just as an additional information nugget, sort of. Let me add that this term, which is dependent on the Berry curvature, is a very important term that is goes into the semi-classical equations of motion. So there are two equations. This one, think of an electron wave packet which is centered at some position r, and you're looking at the evolution of this wave packet, how the position vector changes in time. So this is given by this first equation. This is the usual group velocity. And then you have this Berry curvature term, which is called the anomalous velocity. It depends on the band structure that you have. It depends on the bands and their evolution. And the second expression equation gives you the rate of change of the momentum in terms of the applied electric field and the magnetic field. So if you look at the old textbooks on solid state physics, like Ashcroft and Berman, you won't find this term there. This is new, and now it's become very, very important and fundamental in studying transport in different materials. So, and in semi-classical analysis, this is the fundamental equation that can be used. And it contains this very important contribution from Berry curvature. So, as I said earlier in the previous slides, the Berry connection and Berry curvature are very important concepts in their own right. That's why now they are standard material in elementary quantum mechanics courses. But they've become very important because they're widely used in condensed matter systems because they're an important ingredient in topological invariants. And the first appearance of a topological invariant was in integer quantum Hall insulator as far as condensed matter is concerned. So the first condensed matter system where topological invariants made their appearance was in integer quantum Hall insulators. So before I talk about quantum Hall effect, just to remind you the classical Hall effect. Classical Hall effect, Edwin Hall, 1979 standard. Everybody knows about it. So we have a metal wire, and if you apply a permanent magnetic field to it, connect voltage to it, drive a current. So because the Lorentz, the charges pile up, and there's a particular electric field, and there's a current going through it in the state. And what you have is a Hall resistivity, and experiment showed that it varies linearly with magnetic field. And this can also be derived very easily using the Drude model, classical Drude model. And this was the classical result. And this measurement is very important because you can determine the density of the charge carriers and the sign of the charge carriers. And it's a standard experiment condensed matter physics. There's quantum Hall effect almost years later, von Klitzing, and like many experimental and theoretical results, there's a role of serendipity in it. So there was von Klitzing wasn't looking for, but he was doing experiments on dimensional electron gas systems. So you have semiconductor structures where electrons are essentially confined to a two-dimensional plane. And these are fundamental of micro computer chips. So von Klitzing was working in the high magnetic field laboratory, and they were testing these systems under extreme conditions. So at very high magnetic fields and low temperatures, so looking for some exotic phenomena that they could harness and use the electronics electronic industry. So while he was doing that experiment, what he found was something amazing. You see that this curve with all these plateaus, this is the Hall resistance. So what you have here is at low magnetic field, this classical result. But if you go to higher magnetic field, and that was the regime that Klitzing was working on in, you get these structures. And the surprising thing is that these this jump from one plateau to another is highly universal and very precisely quantified for different samples. I mean, these were not samples. These were semiconductor samples where there was disorder. Even you could have all kinds of impurities, and you were making all different types of connections to do the measurements. And the shapes could be different. Even then, what he found, and he checked it continuously because it was a very surprising result, that this quantization is universal. So sample to sample, you get this very precise quantization. And it is accurate to 1 in a billion. So the decimal place. What I'm talking about is these values, one plateau to another. It's a universal result, and it's a satisfied. And since this result is seems to be so robust and universal, so there was a sort of a hint that probably plays a role. And the first person to actually connection was David Thouless. This is part of the reason he won the Nobel Prize in 1960. So let me just mention one thing before I try to explain this thing, is that when we, like I said earlier, Berry connection, Berry curve, important concepts. And here when we determine the Berry connection, the block functions, because in condensed matter systems, we're looking at these where the basic electrons are block functions. So one given a block functions, one can calculate the, and from that the Berry curvature, and we'll find that these two quantities play a role in understanding topological properties such as that of the integer quantum Hall insulator. To understand that a little bit, let's consider a two-dimensional, because the integer quantum Hall insulator is a two-dimensional system. Electrons are a two-dimensional surface. So in that case, one can think of the Brillouin zone as a two-dimensional surface. This is 0 to 2 pi by, I've taken a is equal to 1. So in this a is equal to is the lattice constant. So you can think of this as a surface. So, and if you, these points related by reciprocal lattice vectors, k is equal to k plus g, g lattice vector. So these are identical points. So if you roll this dimensional surface and join these points together, what you get is a two-dimensional torus. And so the two-dimensional Brillouin zone has the topology of, and so at this stage one should be making between the figure here and the one shown in an earlier slide discussing Gauss-Bonnet theorem. And what is something is very similar here. There we were integrating the Gaussian curvature over the two-dimensional surface of either a sphere or a torus. Here we are integrating the Berry curvature, which is the curl of the Berry connection, overall another two-dimensional surface, which is the Brillouin zone, 0 to 2 pi by a, 0 to 2 pi by a. And it also turns out to be quantized. If you do this integral, keeping in mind that these block states are identical at these points, you find that, very short derivation, you find that this quantity here turns out to have integer values, and it's quantized. So Thalos, Kohomoto-Nins, and Nightingale, they wrote a very influential paper in 1982 where they showed the same thing, that the Hall conductivity, extreme quantization of Hall conductivity that von Klitzing found in experiments can be explained if we, on the basis of topology that is related to topological invariance. And this was the first topological invariant that was realized. And this is what is called the first Chen number. The first topological state in condensed matter system was quantum Hall insulator, and the explanation from these luminaries in terms of this topological invariant is the first Chen number. So here the Brillouin zone plays the role of the surface, and the curvature is the you're looking at the block states, how they curve in terms of the Berry curvature. Now, understand the quantum Hall insulator because it's useful, because it sets the stage for everything else. In a semi-classical picture, when you have these electrons moving in a two-dimensional plane, you have an applied external magnetic field in the z direction. So electrons are moving in the xy plane. So these electrons perform this circular motion. But at the edges, what happens is they cannot complete their circular motion. They have a skipping orbit. So the electrons move in a unidirectional way on these edges. So think of this as there's infinite in this direction, but confined in this direction. So on the edges, there are unidirectional motion of electrons. This was the classical picture. So it tells you that there is some edge modes in this system. The two edges, there are modes which are confined to the edges that carry current. Because after all, we are calling them insulators, but they're not your usual band insulator because you're getting a finite conductivity, and try to explain where this finite conductivity is coming from. So it's coming from the edge states. Quantum mechanical picture, as you know, the electrons, magnetic field in the z direction, electrons are moving in the xy. They form Landau levels. They occupy Landau levels. So think of this as an occupied Landau level. And if your Fermi level is gap here, there's the edge state that is intersecting the Fermi energy, and that contributes to the edge current. And similarly, same picture thing I'm just trying to explain again is that these are the Landau levels, and if confinement potential, the Landau levels bend upwards. If you have Fermi level in the gap between two Landau levels, you see that in the bulk is insulating because no states are crossing the Fermi level. Whereas on the edge, the Landau levels that bend upwards, they cross Fermi level and contribute to the edge currents, contribute to the conductivity. So this is, since it's in this direction, the current in this direction is for the right movers and this is for the left movers. So on one edge you have unidirectional current in one direction, and then you have opposite direction at the other direction. So important to, and this is, you see again and again, that a topological field has an insulating bulk. An example of that is in this quantum Hall insulator, and chiral unidirectional edge states, or if you have a three-dimensional sample, there will be surface states that are conducting. And the Chern number, the number n that we in the previous slide, is related to the number of edge modes that you have. So there's a bulk edge correspondence. So basically, all of these things I've already said. And so the important result and facts about topological phases is that they have quantized responses, which is rho. So from a quantum Hall insulator, we can a lot of these universal features of topological phases. One of the consequences of being in the topological phase is that the response is quantized and it is robust. Robust in the context of these quantum Hall insulator means that a disorder would not backscatter edge modes, because for backscattering, the edge will have to, there's no edge modes going in the opposite direction on the, so they have to go to this end. And since if you have a large enough sample, backscattering is exponentially suppressed in the dimension. The dimension is large enough. So in the same say, you'll see happening over and over again that the responses are quantized and robust. It's not easy to destroy unless you are hell-bent. And the second thing, a very important consequence for edge or boundary modes. So just as in the earlier slide, you had a genus Z, which was a sphere. You can have a, which is a trivial insulator, not a topological insulator. You can, in n is equal to 0. Just think of this as small n. N is equal to 0. If Chern number is 0, that's a trivial insulator. There are no edge modes which will contribute to conductivity. But on the other hand, if there's n is equal to 1, there will be an edge mode which is contributing to conductivity, and that would correspond to analogy with topology, would correspond to a genus 1. So it's just you don't have to take it literally, but so after the insulator was discovered, it took for people to understand it and appreciate that it had a topological role in it. But there were various questions that were raised in the, and related to topological phases. One, topological phases even in the absence of applied magnetic field. Note that for a quantum Hall insulator, you need a. But the question is, can you have a topological phase with? So all these Landau levels and all this classical and quantum description in terms of I gave you earlier that there was a magnetic field applied perpendicular to. Without that, you won't have a quantum integer quantum. So the question was, can you have a topological phase like a quantum Hall insulator where there's no magnetic field? Actually related to a symmetry, which is a time reversal symmetry. Symmetry. So the question can be made more general in terms of whether you can have a topological phase that preserves time reversal. That is one question. Another question is, can you have topological phase dimensions higher than 2D, for example, 3D, or in 1D? Because quantum Hall insulator that we discussed earlier is specifically a two-dimensional system. And do topological phases also exist in metals, for systems which have no gaps? So that was another very important question. And in fact, it turns out that the answer to all these questions is yes, and it took a while for the community to arrive at that answer. But let's quickly go over some of these. In all of these, and there's an important role of symmetry. So we're talking a lot about topology now. We started with symmetry, with Landau symmetry breaking theory. Then we turned to topology and saw what its role was in extreme quantization in topological, in integer quantum Hall insulator. Now we're bringing in symmetry back. And like I said earlier in the previous slide, that can you have topological phases without applying a magnetic field? In other words, can you have it without breaking time reversal symmetry? So two very important symmetries and are time reversal and inversion symmetry in characterizing these topological materials. And these materials are, since symmetry plays a very important role here, they're also called symmetry protected topological phases. Symmetry protected topological phases. What does time reversal do? Time reversal basically means you're reversing the arrow of time. So R remains the same position vector, while the momentum takes a negative sign under time reversal. Because momentum is the derivative of position with respect to time. So if you send time t to minus t, p becomes minus p. And since spin angular momentum, so angular momentum is also, as you know, r cross p. So if r doesn't change, is invariant in time reversal, and p takes a negative sign under time reversal. So spin is also, for electron, you can think of spin as flipping. So spin up projection goes to spin down. Quantum mechanical, you can think of it as complex conjugation and spin flip. So if you think of a plane wave going in a positive, for one dimension, positive x direction, you flip p, make it minus p, you can think of it as going in the negative direction. So it's complex conjugation flip. And an important consequence of time reversal you see is what's known as Cramer's degeneracy. And I'll talk about it in a second. Important symmetry is inversion. I'll not talk too much about it, but it plays a very important role. Under inversion symmetry, you basically, or parity, you basically send R to minus R. And since P is dr by dt, so send not T, but R to minus R, it also makes P goes to minus P, and remains the same. It's not affected by that. Because R and P both flip, so S remains. So important is the Cramer's degeneracy. What that means is that if you have an energy spectrum in a system which consists of half-integer spin particles like electrons, the energy spectrum is doubly degenerate at these points, k minus. Under time reversal, k goes to minus k, but you only define the k value up to a reciprocal lattice. So at these two, the energies of the state, so they are degenerate. And an important consequence of that is that there are certain momenta which are called time reversal invariant momenta. Where if when you send k to minus k, you get to the same point up modulo the reciprocal lattice vector, and up to a reciprocal lattice vector. What that means is, if you send from one dimension, you have these 2 points. 0, k is equal to 0, is equal to pi by a. So the Brillouin zone and the boundary. And if you send 0 to minus, it will still be 0. And it will be the same point up to the reciprocal lattice vector. Send pi by a to minus pi by a, but if you add the reciprocal lattice vector to, you will get the same point. So these 2 points are time reversal invariant points in momentum in the Brillouin zone. So these play a very important role. So there's a degeneracy which is a consequence of Cramer's theorem. So there are 2 degenerate states which are called Cramer's pair. This is what I said. So in 1 dimension you have 2. In 2 dimensions you have 4. So it always goes 2 to the dimension. 3 dimensions you have 8 time reversal invariant momenta. So the question is, can you realize time reversal invariant topological insulators? And Kane Millay in 2005 is possible, but what you need, they had a model very similar to graphene, in which they introduced spin-orbit interaction, but of a very special form, which conserved spin. And they showed that you could get a topological insulator. You could get quantized conductivity in that system without time reversal symmetry. In other words, without introducing a magnetic field or magnetic order into it. But what important ingredient in this was spin-orbit interaction. But this was more of a model, and actually experimental realization was in mercury telluride and cadmium quantum wells. So you had these quantum wells, and if you look at this, when the well width is changed, you go through a phase transition where the bands are inverted, and you go into a topological. So what they found was that you could have these edge modes, like we were talking about earlier, but polarized edge modes. So there's a gap. So if you have a level is in the gap is insulating. The only conductivity comes through these polarized, or what we are also called helical edge states. And you can see that this is time reversal invariant, because if you flip the direction, if you invert the direction, you have to invert the spin also. So you get the same configuration. But for a quantum Hall, it was the edge currents were unidirectional. If you change the direction, opposite direction. So that was not time reversal invariant. Explicitly broken by the magnetic field. That's it. But here it is time reversal. And so this is also called the quantum spin Hall insulator, the topological insulator. And another beautiful result was that as long as Cramer's degeneracy is there, as time reversal invariance is there, this degeneracy, these form Cramer's pairs, like I said earlier, and this 0 is one of those points. And time reversal invariant momentum, this degeneracy cannot be lifted. You cannot go into degeneracy lifted where the edge states merge bulk. That's not possible as long as time reversal symmetry is not broken. This is another instance of where I was mentioning earlier that the response is also robust. As long as the symmetry is present, that response will get that response. way to see this. So for quantum Hall insulator that we discussed, integer quantum Hall insulator that we discussed earlier, reinforce the Chern number. But here, the topological invariant topological invariant. So it only has two values. Identifies the two values identify whether you're in the trivial phase or logical phase. So think of these surface states because these are invariant system. So let's look at the consequences of these surface states on the time reversal symmetry on the band structure of these surface states. So because like this point here, gamma A is k is equal to 0, and gamma B is pi by A. The Brillouin zone, because we're talking about time reversal symmetry, so the Brillouin zone is, and the band structure is symmetric in the negative k direction. So only this direction is this part is being shown. Because these are Kramer's degenerate pairs, so they have to meet here. So you can have one configuration like this. This surface state at these points joins the other surface states because they form Kramer's pairs. Same goes for this. But there is another configuration which is also possible, that the surface states join like this, then they join like this, and then they join like this. And these surface states are connecting the valence and conduction band. Now, the basic difference between the left and the right panel diagram is that if you have your Fermi level in this, on the left panel, if you move your Fermi level, you can move the Fermi level. Or if there's some impurities in the system, these surface states can move down such that your Fermi level will have no states crossing. In other words, it will become a band insulator, not a topological insulator, a band insulator. Whereas in the right diagram, there's no way that you can achieve that. Wherever you place the Fermi level in the gap, it will always cross these surface states. And the important thing, another fact is that there will be even crossings here and odd crossings here. So you can identify even crossing and you can call it 0, and odd crossings you can call 1 modulo 2 and even 0 modulo 2. And these will become your sort of invariants that identify the trivial, this is the trivial, this is the diagram for the trivial phase, and this is the band diagram for the topological phase. So on the basis of Fermi level crossings, one can identify a topological invariant, which is now called Z2 because it's a group with two elements, 0 and 1, and you can identify this. So this is another instance where you have a topological invariant. There are detailed calculations that you can perform and do that, but I just wanted to give you a pictorial view. So another question can be, how do you accomplish a topological phase transition? So you accomplish a topological phase transition by somehow closing the gap. When we talked about topology in the context of surfaces and objects, we were talking about local perturbations and those local, and we did not allow any drastic perturbations. Here, local perturbations means that you're adding some terms to the Hamiltonian, and you're looking at how the band structure changes as a result of those terms. So that is you're the Hamiltonian, which is describing your system. You don't have a surface that you're physically deforming in some way. And when you talk about cutting and pasting and making holes, that corresponds to closing the gap when we talk about gap in the bands when we talk about topological phase transition. So you have a band with some Chern number, you have another some Chern number. So think of all the rest of the bands are not important. You're only looking at two relevant bands close to the Fermi level. And you change some parameters in the system, you tune the system somehow. Like for example, for Mercury quantum wells, you're changing the width of the well. you go through a phase, you find where the bands cross, and then the bands open again. So this is what corresponds to a topological phase transition. And this topological phase transition, the sum of the Chern numbers remain the same. And usually what you find is that the bands inverted with some of the Chern numbers remaining the same. So I'm coming to my last. And so another question was, can we have topological isolators in dimensions higher than 2? So yes, they've been theoretical. There were theoretical proposals, and then there were realization. And there are two types of 3D topological insulators. One of them are known as weak topological insulators. They're essentially stacks of 2D topological insulators. And then you have strong topological insulators, three-dimensional topological systems. And to characterize the topological and trivial phase, one can use the same Z, but you have to generalize it. So you should have like 4 Z2 invariants. And first experimental realization was bismuth antimony, and then bismuth selenide and many other materials, compounds were found to be three-dimensional topological insulators. A special feature, like I mentioned earlier, for 3D topological insulator. Any question, Sabeeh?
Kashif sir, I
I'm
just
just
wanted
coming
to,
to the
right,
slide.
5, can we wind up in 5 minutes if possible?
Yes, sure. I'm just,
Thank
I'm at that, like 2 or 3 slides. And quick.
you. Thank you. Thank you.
So realization of these three-dimensional topological insulators. And another question was, can we have topological insulators in matter, in phases of matter where gapless phases? Because we talked about Chern numbers and Z2 invariants have the Fermi level in the gap. So gap played a very important role in defining this. But now the question is, and surface states played a very important constant for surface states. But if you have a metal and gap in the bulk, you would expect that the surface states would merge with the gap and you would have robust surface states. But what has been realized recently has been that there are what are known as ones, and these have these while nodes where, like Dirac nodes, where while nodes with conduction valent bands meet. And the surface states are very special states, which are open surfaces on. So part of the Fermi surface is on the top and part of the Fermi surface is the bottom. So they form a, but they are disjointed Fermi surfaces. The transform, and these are called Fermi arcs, and they join these while nodes. And one can define the Chern numbers and all that on the same footing. Last is superconductivity. There was a very model given and by Kitaev of 1D waves. And the important and the reason that it sort of captured the community was that he showed that if you have these electrons with a special superconductivity, wave superconductivity pairing, you could express the model in terms of Majorana fermions. State where one of the phases was, which is called the strong coupling phase, where you can have Majoranas at the end. So Majorana fermions are you can think of Majorana fermions as Majorana fermion state is a linear combination of whole state in this context. And these were important, and actually there was their own antiparticles, and there are pinned at the end of this one chain, and their energy is zero, called 0 moles. And another interesting thing is that they're still called non-abelian statistics. So they're not fermionic or bosonic statistics. they have an ionic static and a very special kind, which is non-abelian. So people are interested in it because one fact is that since they are and two Majoranas, they always come in pairs, and two Majorana fermions make up an electron or a fermion. So if you want to encode information, you can encode information in a single fermion. You can say no fermion or one fermion state. So you have a qubit, basic ingredients for a qubit. And that information can be encoded in these two known local degrees of freedom, the zero mode states, the Majorana states. And since these have non-abelian chain statistics, so they are not prone to local perturbations, in the sense that, the greatest challenge in quantum computation is that the quantum states are very fragile, and so any kind of local perturbation, a stray photon, anything can collapse the coherence of a position that you have. So if this information is encoded non-locally, there's a hope that it would be useful and more robust as far as topological quantum computation is concerned. So there was a proposal, theoretical proposal, that you could have Majorana fermions in a semiconductor nanowire with strong spin orbit coupling, this screen is a superconductor like aluminum, which is in proximity to it, and you apply a magnetic field, you can create that same situation that I have predicted here, and you can get that situation. And experiments carried out in Netherlands, the Delft group, what they did was they had this nanowire, and but there's no evidence as such because you look at the zero bias due to tunneling conductivity, and you have to look at the zero bias for it, and there are other sources of it. And so last slide, and which is what has been left out. I've left out a lot, so I've just covered sort of some of it because the vast field. What has been left out is that I've only discussed equilibrium system, topological phases, which are non-interacting. So I've left out all the interacting phases, which are in itself very interesting phases, but it's a field, some parts of it to be left out. And the second thing that I've left out is I've not discussed non-equilibrium topological phases. So it's a very important current interesting area of research where you drive the system out of equilibrium, create topological phases like through Floquet engineering. You can have Floquet topological insulators where you shine light on these, and trivial insulator can be converted into a topological insulator. So with that, I want to thank you for your patience, and that's it.
Thank you, Dr. Kashif Sabeeh, for this excellent talk. I think this serves as a very important primer to the subject, and anyone who would like to get started, this just is a comprehensive overview in the 1 hour. So thank you very much for all of this. So if there are any questions, please feel free to ask Dr. Kashif Sabeeh.
Sir, I have two questions. So usually we are having these topological phase transition by external stimuli like magnetic field, electric field, doping, pressure, etc. Can we drive these transition by phonon modes? And the second question is to drive these topological phase transition, we have to break the time reversal symmetry and inversion symmetry. Can we do this by only one type, by breaking one type of the symmetry?
Thank you, Zamil. Very good questions. One regarding phonon interaction, electron-phonon interaction driving a phase from a trivial phase to a topological insulating phase, something very interesting. And in fact, Ian Garate wrote a paper a few years back where he discussed how raising the temperature you can also, because by raising the temperature, the more phonons in the system, and you can drive the system a trivial phase to a topological phase. So that proposal is already there, and if you're interested, to the reference where they show that there is a topological phase transition because of phonon interactions. And coming to your second question, if you think about, let's think about graphene for a second. Graphene, in the absence of, in the presence of both time reversal and spatial symmetry, is not a topological insulator. But you can drive it into a topological phase, like Haldane had done, by breaking these symmetries. And also, you can either break, for example, spatial inversion symmetry by the on-site, by changing the on-site potentials on lattices A and B, lattice A and B, for example, through substrate. And what that does is breaks inversion symmetry. And because for a topological insulator, you need a gap. Topological insulator, if you're not talking about topological metals. So go into a topological phase by either breaking inversion symmetry or breaking time reversal symmetry. And these are possible routes to topological insulating phases, because both of these lead to opening of. Because if both of these are present, then your system is gapless. For example, if we talk simple dark material, it will be gapless.
Thank you, sir.
Thank you. Any more questions? So with this, I would really like to thank Kashif Saab for this
My pleasure.
talk. बहुत शुक्रिया.
My pleasure. Thank you for the invitation, and see you tomorrow.
Inshallah.
World.
Thank you. Thank you. Khuda Hafiz.
Inshallah.
So we also have one last talk, and that is by Dr. Nasir Mahmood. It would be really nice if this could be done in the stipulated 30 minutes, including the question answers. So a 20-25 minutes talk would be really nice. Dr. Nasir Mahmood is currently at the Kohat University of Science and Technology, and the topic of his talk is Husserl alloys investigated through density functional theory and artificial neural networks. So over to Nasir Saab.
Assalamu alaikum. Thank you very much, sir. And I will try my best to complete my talk and this particular given time. Especially before starting this, I am going to thank you all to include me. You have included me in this session, and now I am going to start my talk. I am Nasir Mahmood, and a PhD student in the Department of Physics, Kohat University of Science and Technology. And I think that I am audible to you all.
Yes, you are.
Okay, thank you very much. And today's my topic of this talk is investigation of half and full Husserl alloys. Okay, and this investigation is basically based on the modeling. And modeling, we have used the density function theory (DFT), and then